of the lesson. Okay, so vectors like displacement, velocity, acceleration, they all have directions associated to them. All you know is that if any one of these quantities is acting in the opposite direction, then you will have a negative sign. But how do you know which one is going to be negative in the first place? It is based on something called sign convention. All right. It is basically a direction which is assumed to be positive. All right. Whenever you're dealing with vectors, you normally need to have something called a sign convention so that you are able to determine what is positive, what is negative. If I just tell you there's 5 Newton versus negative 5 Newton, all you know is that this is opposite to this. But what direction is this specifically? You do not know. But what if I told you that you assume that going towards the right is positive? So what you would then know is that this 5 Newton is going towards the right, but the negative is going towards the left. Or if I tell you going upwards is positive, then what you can interpret from this is that the 5 Newton is acting upwards, but the negative 5 Newton is acting downwards. That's what sign convention actually is. All right. Now, there are a few cases here for you to determine positive and negative directions for all the different quantities. Let's just start with displacement first. Now, let's just assume that there are 8 different cases here, and this point here is your reference point, or you can think of it as your starting point. All right. Your sign convention is going towards the right as positive. When it comes to displacement, whether it's going to be positive or negative, which direction is positive, which direction is negative, depends on which side of the reference point the object is at. If this part here, I say, is my reference point, let's just assume that over here is considered to be positive displacement, then over here is considered to be negative displacement. Whatever objects that I have on this side of my reference point, on the right side of my reference point, they will all have positive displacement. On the other hand, if the objects were on the left side of my reference point, they will all have negative displacement. When it comes to displacement, what you really look at is just the side of the reference point it is at. Okay. Like for example, if you look at this case here and this case here, this is positive displacement. Sorry, not this case. This case. I'm talking about more of this case. You look at the first case here. This case here, you have positive displacement. But then this other case here, the third case here, you see it's also positive displacement, but it's moving in the opposite direction. We still call it as having positive displacement. All right. It really depends on which side of the reference point your object is at. That is the gist here for displacement. Now, for velocity will depend, the velocity direction will depend on your direction of motion. Whether it's going to be positive or negative depends strictly on the direction of its motion. So right now, we say that going towards the right is positive. You look at the 8 examples here, any of the objects that is moving towards the right, that is following the direction of the sign convention, will have positive velocity. On the other hand, any object that is moving towards the left, opposite to your sign convention, they're going to have negative velocity. So in this case here, for velocity, positive or negative is strictly dependent on your direction of motion compared to your sign convention after that. If it's in the same direction as the sign convention, it will be positive. If it is in the opposite direction to your sign convention, it will be negative. That is for velocity here. Okay, you could have negative velocity but positive displacement, like this example that you see here. It's positive displacement because you're on the right side of your reference point, but it's negative displacement because you're moving opposite to your sign convention. All right. And then lastly, Acceleration direction, whether it's positive or negative, depends on your net force, the direction of your net force. This one here relates to what you learn in Newton's second law. You learn in Newton's second law before this, F net is equals to ma, all right? So what this means is that the resultant force causes an acceleration for a given mass. The thing is that the net force is always in the same direction as A, as the acceleration. Okay, if your net force is in this direction, your A would be in this direction too. If your net force is in this direction, your A will also be in the same direction. So this is one thing that you need to understand first. Whatever direction of acceleration you have will always be in the same direction as your net force. Okay, so here we say the acceleration direction depends on the direction of the net force. How do you apply it to this case? Now, if you look at the cases on the right here, specifically this one here. Now, before this, I mentioned to you how to look at whether an object is going to be speeding up or slowing down by looking at the direction of the acceleration with respect to the direction of motion or velocity. That one is under this page. This one is under pages 4. We talk about what happens to the motion of an object when acceleration is the same direction of motion, is in the opposite direction to the motion, if it's perpendicular to it. So that one, you will use it here, okay, in the example that you are doing. Okay, page 7 here. Now you see for the right hand side here, the speed is increasing, okay? Your speed is increasing here could mean that your F net is in this direction, your acceleration is in this direction. This is the thing that causes your speed to increase, all right? So your acceleration is in this direction, going towards the right. If you compare it to the sign convention that you have, going to the right as positive, this is in the same direction as the sign convention, so this is positive acceleration, okay? Now, if you look at the other case, the part where the speed decrease, the only way your speed would decrease is if your acceleration is opposite to your motion. Okay, your F net is in this direction, your acceleration is in this direction. Now, looking at the direction of your acceleration now, it is opposite to your sign convention, so this is negative acceleration. Then you move to the case below there, the speed is increasing, but in this direction. The only way that the speed can increase in this direction is if your net force is in the same direction, causing an acceleration in that same direction. Your acceleration here is opposite to your sign convention, so it's negative acceleration. Then you look at the last case, the speed is decreasing while you're going towards the left. This would mean that your net force and hence your acceleration must be acting opposite to your direction of motion, causing the speed to decrease. When you look at the direction of your acceleration with respect to the sign convention, it is in the same direction. So this one will be positive acceleration. That's how you determine whether the acceleration is going to be positive or negative. You have to first see the direction of the acceleration, then compare with the sign convention, then only then can you see whether it's positive or negative. And a lot of times, to see the direction of the acceleration, you would also relate to the net force acting on the thing. The net force is the one that causes the acceleration, and the acceleration will always be in the same direction as your net force. Okay, now, when you have a negative, sorry, let's go back to the other. This is a bit hard to see, right? Okay. Now, if you try to apply the same analysis to the left one, to the left side here, you will eventually come back to the same conclusion that acceleration is positive, negative, negative, positive here. All you just need to do is to just work out the direction of your acceleration. If speed is increasing in this towards the left, sorry, towards the right, your acceleration is in this direction. If speed is decreasing towards the right, your acceleration is in this direction. Speed increasing towards the left, your acceleration is in this direction. Speed decreasing towards the left, the acceleration is in this direction. That's how you got the respective signs of your acceleration. Okay. Now, just because an acceleration is negative, it doesn't mean that an object will be slowing down. Previously, you might have learned that you may have thought that if you get negative acceleration, that means the object is slowing down. But that is not really the case here. You could have cases where you have negative acceleration, but the object is actually speeding up. Okay, what do I mean by that is this. You see these cases here. This one is negative acceleration, but the speed is increasing. And then this one is also negative acceleration, but then the speed is increasing. So here you see the acceleration is negative, but the speed is increasing. You're not slowing down, you're not decelerating. So just bear in mind that just because acceleration is given the sign negative, it doesn't necessarily mean that it could be slowing down. It could also mean that it is speeding up. A more accurate way of deducing whether something is going to be speeding up or slowing down is by looking at the signs of the velocity and acceleration. The next page I wrote it there. If you want to see whether something is speeding or slowing down, you just look at the sign of the velocity and acceleration. If the velocity and acceleration have the same sign, either both are positive or both are negative, then the object is speeding up, because this would imply that the direction of motion is in the same direction as the acceleration. On the other hand, if your velocity and acceleration have opposite signs, one of it positive, one of it negative, the object will be slowing down because the acceleration is opposite to the direction of motion. What do I mean by that is you just look at the few cases here in the previous page. You see this one, velocity and acceleration positive, same sign, speed increase. Velocity and acceleration, opposite sign, speed decrease. Then velocity and acceleration, same sign, both negative, speed increase. Then the last one, velocity and acceleration, opposite sign, speed decrease. Okay. When you have opposite signs, it already means that your velocity and acceleration are in opposite direction. If you want to look at it over this diagram, your velocity is in this direction, your acceleration is in this direction. For the second one, your velocity is in this direction, but your acceleration is opposite. Then for the third case, your velocity is towards the left, your acceleration was also towards the left, both same direction. Then the last case, velocity is towards the left, but acceleration is towards the right. They are in opposite directions. So this one will tell you why they are speeding up, why they are slowing down. Okay, this is one way of looking at the signs. Okay, then we go to equations of uniformly accelerated motion. This is what you learn as your SUVET equation, or some people call it as kinematics equation. Now, there will be four main equations that you will need to know for this chapter. That one is your kinematics equation, and you need to know how to derive them. Your questions require you to know the derivation. They are normally derived from this graph. All your equations of motion, the kinematics equation or the SUVET equations, v equals to u plus at, s is equals to half u plus vt, or s equals to ut plus half at squared, v squared equals to u squared plus 2as, they're all derived from this same graph. Okay, these equations only apply for something that is moving with a constant acceleration. Okay, when something moves with a constant acceleration, the velocity time graph would normally look like this. You go from an initial velocity u to a final velocity v, and then the gradient of your graph would be constant. because you learned before this, acceleration is the gradient of VT graph. If your acceleration is constant, that means your gradient must be constant. So that's why here you see your gradient is actually a constant. It's from here that you derive out all the 4 kinematics equation. The first one is actually based on the definition of acceleration from gradient of the graph. Okay, A is equals to gradient of the graph is equals to V minus U divided by T. So eventually you get V equals to U plus AT. This is the first equation derived from the gradient. Then after that, you also learn something else where we say that displacement is error under your VT graph. So if you look at the area here, this is the area of a trapezium. You need to take this height plus this height multiply with this length. So it will be half U plus V multiply with T. This one is the second equation for your kinematics equation. And then from there, what you then do is that you sub one of them into the other. If V is equals to U plus AT, you sub it into here, the second equation. Eventually, you will get back this same, eventually you get back the final result as S equals to UT plus half AT squared. This is your third kinematics equation. For your fourth kinematic equation, what you do is that if originally here you sub for V, what you want to do now is that you sub for T. Here you sub for V into the second equation. You can also get another equation if you sub off for T. All right. So what you do here is that from V is equals to U plus, from A equals to V minus U divided by T, you make T the subject, it becomes V minus U divided by A. Then this one, you sub it inside S equals to half U plus VT, the second equation. Eventually, you get back this result. When you sub it in, you notice that this one is V plus U, V minus U. This has something to do with what you've learned in maths before this. If we say A squared minus B squared, that means A plus B, A minus B. Right now, you have a case where it's V plus U, V minus U. So it's going to give you V squared minus U squared. So for S equals to half U plus VT, once you sub in for T, you're going to get this expression here, which in turn simplifies to this. And then you try to simplify it further, you're going to simplify it further by moving the 2A here, you're going to get V squared equals to U squared plus 2AS. This is your fourth kinematics equation. All right. The last one isn't so common, but it does come out in your past year exam before. You notice that between this equation and this equation, they somehow share the same form. There's something like a similar pattern to them. The only thing that's different now is that whereas this one was U, this one was V. Whereas this one was positive, this one was negative. So how did this one come about? It comes from the different variable that you substitute. For the third equation that you see here, you got this by subbing V equals to U plus AT into here. All right. You're trying to get rid of V. That got you this resulting equation. If you want to get the fourth equation here, sorry, not the fourth equation. You want to get the fifth equation here, what you do is that rather than subbing for V, you sub for U instead. Okay, what you do is that from this equation here, V equals to U plus AT, you make U the subject, U is equals to V minus AT, and then you sub it inside here. Eventually, you get back this final result. S is equals to VT minus half AT squared. This is the fifth equation that you Boolean. Okay. The more important one is to know the four. The first four, this four. The fifth one is tested also, but it doesn't come out that often, but it's useful to know. All right. So all these kinematics equation can only be used under one certain conditions only. Under constant acceleration case. If you see that the objects experience constant acceleration, these equations will always apply. On the other hand, if you do not have constant acceleration, you cannot use these equations. Okay, just bear in mind that these equations can only be used for cases of constant acceleration. All right. Now, you have a stone that is thrown vertically upwards at the speed of 5 meters per second from the edge of a cliff. Assuming the air resistance is negligible, calculate the time taken to reach maximum height. Now, in your case here, if you look at the stone that is being thrown upwards with an initial speed of say 5 meters per second square, you can easily visualize what would happen to the stone. It will go up, and then after that, you eventually stop at maximum height, and then after that, it will eventually fall downwards. Okay, so this is what we can see from here. Now, at maximum height, this part here being your maximum height, one of the things you can actually say from here at maximum height is that V is always 0. Okay, because you see your object, when it goes up, it will be at the just right before it reaches maximum height, your object is moving up. And then after that, just right after it reaches maximum height, it will go down. All right. So at the point where you reach maximum height itself, the velocity will actually be 0 because you have to stop momentarily. Okay. Because stone has to stop momentarily before changing directions. Before changing directions. Okay, so this is what you can use to deduce why your velocity is going to be 0 at maximum height. Okay, now at the same time, there's also one thing that you can probably try and see from here. Now, when you are going upwards in this direction versus when you're going downwards in this direction, different color, versus when you're going downwards in this direction, when you are going upwards, you will actually be slowing down. Your ball is actually, not the ball, the stone, you will actually be slowing down. Okay, when you're going upwards. But then when you're going downwards, you will actually speed up. Okay, so here, if you see that the question already mentioned to you that air resistance is negligible, the only force acting on your object right now is actually just the weight. Okay, I can tell you that if you were to look at this point, this point, this point, this point, or this point, the only force acting is really just the weight. So from there, I can actually just say that throughout the entire motion of this object, you are actually experiencing a gravitational acceleration of G. Okay, so it's because I know that the gravitational acceleration G is acting downwards that I can actually deduce whether something is going to be speeding up or slowing down. Because you see, in my case, when I first project the object up, it's moving upwards, but my acceleration is opposite to my motion. So I know it will slow down. And then after it has started to move downwards, my motion is downwards, my acceleration is also downwards, same direction, therefore I know I would speed up. Okay, so this is what you can actually kind of visualize from the question. Now, if you go back to the question itself, where we tell you the time taken to reach maximum height, you can make use of your kinematics equation. Okay, because just now I mentioned to you the only force acting is your weight. So you are going to experience gravitational acceleration G. And that acceleration is the same throughout your motion. So it can be considered as constant acceleration case. So when you have constant acceleration case, you can always use the kinematics equation. Always this form. Okay, these are the most simple basic form of your kinematic equation. Right, it's always this one. Okay, so let's look at part A then. Now for part A, one of the ways you can do is that you always try to work out what are the variables you know, what are the variables you do not know, and for the variables you do not know, which one is it that you actually want to know, and which one is it that is actually unwanted. So what I mean by that is this. Say for example, right now, for part A, I know that my initial velocity is 5 meters per second because it's already stated here. At maximum height, I know that my final velocity would be 0. Okay. Now, do I know the time taken for me to reach the maximum height? Nowhere in this question did they ever tell you the time taken. All right. And also, do you know the distance to maximum height when you first project it to the maximum point of maximum height? You also do not know, right? So the S representing displacement is also unknown. Okay. Now your acceleration is already known as G lah. Okay. So these are the few things that you can see here from that part. Now you have two unknowns, T and S. One of this is something you actually want. One of this is something that you actually do not need. So in the context of your current question, you actually want to find T, but S is not something that you want. Even though it's not, even though you do not know what it is, you also do not want to know. Okay, it's not required by your question. So you compare with your kinematics equation. Any equation with an S would not be something that you want to use. So that automatically eliminates equations 2, 3, and 4. So you will have to use equation 1. Okay, so you would need to use this equation V equals to U plus AT. Now, last week I also mentioned to you when you are using kinematics equation, it is always important to have something called a sign convention to indicate a direction which you assume is positive. So that time I mentioned something like this, where I say that when using kinematics equation, always set a sign convention. Okay. Then I mentioned to you sign convention follows or tends to follow initial direction of motion. Okay. Initial direction of motion. Okay. So in your case, we know that the object was originally being projected outwards. So I will actually say that going outwards is positive for me. Okay, so anything in your equation right now that points upward will be positive. Anything else that points downwards will be negative. Okay, because you have to compare with respect to your sign convention. So now if I start to replace out my values, V would be 0, U would be 5, and then my acceleration would actually be negative 9.81 times T. So that T would actually be, where's my calculator? T will actually be 5 divided by 9.81, giving me some value. Wait, my calculator is not around. Wait, can you just give me 1 minute? I go and take my calculator. It's downstairs. Right. So just let me pause the lesson. Yep. Okay, right. So sorry for the delay. Okay, now the time would be 5 divided by 9.81, giving you 0.51 seconds. Okay, so you want to follow the EJU style of doing things, basically T would just be S over G though. Okay, since EJU always tends to want the answer in terms of a variable. Okay, now let's move on to part B. Now for part B, where they tell you find out the velocity at t equals to 1.2 seconds. So you can actually kind of do that same analysis again, where you try to work out what are the things you know, what are the things that you do not know. So in your case, for part B, same thing. I know u is 5 meters per second. V is what I want to find right now. T is known as 1.2 seconds. A is equals to G. And then distance, or rather the displacement, is not something I know. So right now, you can see that there are two unknowns. One of this is what I want. One of this is not something I want. So V is actually what I want right now. But displacement is actually not something I need. Okay.
Can you use like the first equation?
Sorry? Yeah, so same thing as before, you are going to use back the same first equation. You are not going to use any others, right? So here, outwards is positive because this is your sign convention. Then you get V equals to U plus AT. You're going to get 5. Sorry, V is what you want. V, and then after that, this one will be 5. This one will be negative 9.81 times 1.2, giving you 5. Okay, 9.81 times 1.2 times 5. Wait. 5 plus negative 9.81 times 1.2. You're going to get the answer is negative 6.8 meter per second. Okay, or rather in the EJU style of doing things again, V will actually just be U minus GT. Okay, right? This is the answer in EJU. Okay, for the EJU style. Okay, now the thing that you can probably try to see here is this. What is the significance of this negative? Okay. Yeah, you see, your positive negative here is made with respect to your sign convention. If you're getting a positive value, it means that your velocity is in the same direction as your sign convention. If you're getting a negative value here, it is indicating to you that your velocity direction is opposite to your sign convention. This one is essentially telling you that your velocity is downwards. Okay, which would actually make sense that this one will actually make sense that your velocity is downwards, because you see, just now we already established that for you to move from here, from the initial part where you project the stone out to maximum height, it took you 0.51 seconds. Okay, for you to reach maximum height in the first place was already 0.51 seconds. But now you are talking about 1.2 seconds, which is actually more than 0.51. So you already know that at 1.2, you definitely have already gone past your maximum height. You would actually now be moving downwards. So when you're moving downwards, your velocity direction obviously is going to be downwards. No? So this negative is actually telling you that, proving to you that it's actually downwards. Okay, so this one is what you can see from here. So there are some understandings to be gained from all this. Right, then after that, you look at part C. Now, what's the position of the ball when t is equals to 2 seconds? You can try to see a few things again. In your case,
Position, are they asking for distance?
now this one is actually asking for your displacement. They're not asking for distance. The distance move is actually the last part. Your current question is actually just asking you for, in part C, it's actually asking you for the position. When they say position, it's actually asking for the displacement. Okay. So in your case, you know U is 5 meters per second. V is unknown. T is known at 2 seconds. A obviously is still G. And then your velocity, and then in your case here, your displacement is again unknown. So there are two unknowns here. The velocity and displacement. So
S
displacement is
equals
what
to
you want.
UT plus half AT squared.
Yes. So let me just get rid of this bit. So anything with a V will be out. This one out. First equation, third equation, second equation out. So the only one that we need to use is the fourth one. Okay. So this one is, again, upwards is positive. So S is equals to UT plus half AT squared. This one will be 5 times 2 plus half multiplied with negative 9.81 times 2 squared. Oh yeah, I think I did not really mention to you why the acceleration when I sum in the value is negative. Now, just now I explained to you already that your gravitational acceleration is always pointing downwards. Okay, so if you compare that direction with respect to your sign conventions that you said, it's actually opposite. That's the reason why it was negative in the first place. Okay, just so you understand why the negative come about. Okay, so this negative is due to the fact that acceleration is opposite to your sign convention. That's all there is to it. Now, if you go and calculate out everything, you're going to get the answer as 5 times 2 plus with 0.5 times negative 4 times 9.81 times 4. You're going to get the answer as negative 9.6 meter. Okay, you're going to get the answer as negative 9.6 meter. Okay, now, if I then do it the EJU style, this one will just be S equals to UT minus half GT squared, just like that. Now, same thing as before. What is the significance of this negative? Now, this negative here is actually indicating to you that you are actually now below the cliff. You see, you actually projected your stone from the edge of a cliff. Okay, so if you look at your cliff, this is where your cliff is. Okay, maybe I should use a different colored line. This is where your cliff is. This is the level that you started off. Okay, this is the cliff, the starting point. Now, in general, we know that displacement is actually a vector. It's going to have direction, it's going to have a positive and negative. So in my case here, you could say that anything above the starting position is considered to be positive displacement.
I think I get it. So yeah.
All right. And this one, anything downwards is
it will be negative because your level of plane is 0.
Yes, correct. So this negative here just means that you are below your starting point.
One thing I'm curious right now is that, like, when do you know like what formula to use? Like example, like in this formula, in this thing, right? Why can't we use the acceleration formula and stuff like that?
Or why can't you use the acceleration formula?
Like example, like
The one where we say A is equals to B divided by T, right?
yes.
Oh, okay. If we want to use,
That's why like I think that's another problem with physics. I don't know when to use what, you know.
oh, okay, let's just go with what you just said. This one A is equals to B over T. Were you thinking to use it right over question B?
Yes.
Okay. Actually, that one by itself won't have an issue, no problem with that. Because you see, by definition, acceleration is delta rate of change of velocity. A is delta V delta T, where A is actually V minus U divided by T. So this one, if I rearrange it, V is equal to U plus AT. You're actually doing the same thing. Okay.
It's just except for the first one, right? The first equation, there's just no way that you can use it because
Yes. For the first equation, you can also still use it for the first equation also.
technically all this equation is derived from A equals to B over T, right?
Yes. The main starting equation was V equals to U plus AT, which in turn came from this. Yes, you're correct in saying that. All these little equations that you see, equation 1, 2, 3, 4, they were all derived based on this. If you remember the substitution that we did in the previous lesson where we showed how to derive all this, the diagram that I mentioned to you, this one here, you keep changing what you substitute into the subsequent equations. That's how you got the different equations. And this V equals to U plus AT actually came from definition of acceleration itself. Okay. So in your case here, if you had just wanted to use A equals to delta V over delta T, you could have actually just used it for A and B. No problems there. It's just that you need to be careful about what you write, because a lot of students from SPM or IGCSE have a tendency to write A is equal to V divided by T, where they just take velocity at some point divided by the time taken to reach that velocity. But what they should have actually known is that acceleration is rate of change of velocity. You need to take the difference in velocities between the 2 points and then the time taken between the 2 points. Okay, so nothing wrong with using A equals to V over T, but just be careful that it's actually talking about change in velocity over change in time.
Because like this kind of question is also very similar to like those questions where they ask you A equals to B over T, you know. It's just that like the difference is very hard to tell in a few ways of one another.
Yes. It is, how to say, I mean, the more questions you do, eventually you understand the context. Right? So like now, I think it's because when you first start off at this level, at pre-U level, there are some things that you bring over from IGCSE or SPM. So in IGC or SPM that time, some understandings were simplified. Okay, that's why when you use that understanding and then you try to use it in EJU right now, somehow it doesn't make sense anymore. Okay, so the reason for that was because there were some further things that you needed to understand, right? Let's just say, for example, the acceleration here. It's not as simple as just saying velocity at a point divided by the time at that point. It's actually the change in velocity between 2 points divided by the time between those 2 points. Okay, right? So that one is really okay. All right, then after that, we go to the last part. So displacement, this one is actually just talking about your distance from a reference point in a specific direction, or rather your straight line distance from a point. So if I were to try and indicate to you the 9.6 meter, it is actually just telling you right now that your 9.6 meter is from here to here.
Yep.
This is your
Yep.
negative
I get that point.
9.6 meter.
I get why is it 9.6 meter.
Okay, right. Okay, then after that, the last part here is where you need to talk about total distance traveled when t is equals to 2 seconds. Okay, now if you're talking about displacement in part C, it is only referring to this length, which was 9.6 from the starting point now. But then when you talk about total distance traveled when t is equals to 2 seconds, the same as that as before, it's actually referring to this length going up and this entire length going down. That is what we mean by total distance. Okay, so to find total distance, there are actually a number of ways we can do that. We know that in general, that object, when it was projected outward, it went up like this, reached maximum height, and then it went down like this. Okay. So what we can actually do is we can actually try to find out what is this distance. Let's just say S1. Okay, now maybe I put it as D1. And then this one here is also D1, right? I mean, if I draw a straight line across horizontally, this side will be D1, this side will also be D1. Okay. And then after that, I can also say that this one is actually D2. So I can say that the total distance then is actually going to be 2 times of D1 plus D2, right? Now D2 you already know is actually 9.6 itself. Okay, because you see it's this thing, this length here. All right. So what you're just left to do is to find out what is D1 in the first place. Okay, so this one, you can actually try to find out the distance to maximum height. If in part A, it was time taken to reach maximum height, right now you want to change the quantity to be found as distance to maximum height. So in your case, you can actually kind of do the same thing again. You know that U is 5 meter per second, V is 0, A is equals to G, and then T you actually already know because the first part you already found it as 0.51 seconds. Okay, so the next one that you just want to find out is the displacement, or rather the distance now. So you only have one unknown here. Okay, so there's no other unknown that is not wanted. So you see that right now you can't really use elimination process like you've done in the previous 3 questions. Okay, so here you want to find out what is S. Any equation with an S would do, since everything else seems to be known already. You can see here. So I can use equation 2. I can use equation 3. I can use equation 4, except equation 1. Okay. So I can use any one of these except equation 1. So for my case, I'll probably just make use of, say,
Equation 2.
Equation 2. All right. So if I make use of equation 2, same thing as before, up is considered to be my positive sign convention. So S is equals to half U plus VT. This one, S is actually my D1. This one will be half. U is 5. V is 0. Time is 2. Then eventually I will get D1 as 5 meter. Okay, from here. Then I also know that D2 is 9.6 meter. So D total would be 2D1 plus D2. In turn, it will become 2 times 5 plus 9.6, giving me 19.6 meter. Okay. So this is what you're gonna get. Now again, if you try to do this in the EJU style of doing things, d total will actually be 2 times of d1, which is half u plus b times t plus d2. So this one cancel off, giving me, and then this one is 0. This one will give me u t plus d2. Okay, so this is what you can actually see from here, right? So this one is kind of a simple example to show you how we use kinematics, but this one you see is straight line motion. Okay, it's just a motion along a straight line. Now, in some of your EJU questions later on, you will notice that your object is moving, but it's not exactly a straight line. It is actually moving in a curve. So when it comes to something that moves in a curve, you will also make use of kinematics equation. All right. So let me just clear this one off. Then after that, move on to the next. Oh yeah, I can't move on to the next part yet because there's a graph drawing in the next part. So let me just clear this one off. Okay, now for your case, if you look at the next part, next page, where we just basically ask you to draw out the graphs of displacement time, velocity time, acceleration time. How are the graphs going to look like? Now, the easiest thing to start with is acceleration, where we say that is a horizontal straight line, which is negative. Okay, why do we say this in the first place? Because just now I told you that your upwards is considered positive. Upwards is positive according to your sign convention. Then after that, your A equals to G acting downwards all the time.
Is this always the case, or is it for the question just now?
This one is the second statement here, A equals to G acting downwards all the time. This one is always it's always applicable if you're talking about an object that is moving through the air and the only force acting is just the weight. Okay. This one, yeah, statement 2 is always applicable all the time. Now, for statement number 1, upwards is positive. This one is actually my sign convention. This one is related to your sign convention. Related to your sign convention. Now, you see, my object just now was thrown outwards. That's why I say positive is outwards. You could likewise have a different case where we tell you that your object is actually released from above and then it moves downwards. In your case, because the initial direction of motion is downwards, so downward is positive. Okay? That's why I told you that this first statement here, upwards is positive. This one depends on context of the question. Okay? So this one depends on question. Okay. And then this one, number 2, this one is true all the time. For a falling object, where the force is just the weight, where the force acting is just the weight. Okay. So because you see my sign convention is upwards, positive, but my G is acting downwards, this tells me that my my acceleration will be negative, isn't it? Therefore, A is negative, and constant. Okay, A equals to G acting downwards all the time. This one already means constant magnitude. Okay, so A is equals to G downwards all the time is actually saying that it's constant value downwards all the time. Okay, so from here I can actually say that acceleration versus time will be negative. Now from here you can actually now start to kind of do some graph changings from one form to another. This one you have to make use of what you learned before, where number one I told you before that change in velocity. Number one, this one is another one. This one is, we mentioned before that acceleration is rate of change of velocity, where the value of acceleration is equal to the gradient of your velocity time graph. Now, if you look at from the previous part, this one to this one of the things that you would have noticed quite clearly is that A is constant and negative. A is constant and negative. So what can I say about the gradient of the VT graph? A is constant and negative. Therefore, gradient of VT is constant and negative too. So it will actually be something that looks like this right now. This is what you're expecting to see. Okay, that's how I got this shape. Yeah, this one actually I could have just wrote it here. Okay, but never mind, I just leave it here. This one I don't think there's any need for me to write number one. Okay, right, so this one is okay. Now then after that I want to go to
gradient of VT,
velocity time graph.
gradient of VT is constant and negative.
Yeah, gradient of VT graph is constant and negative, which is actually this thing right over here. Okay, right. Okay, then after that, I want to go from VT graph to displacement time graph. So this one, I have to make use of another different equation, where I first say that in the first place, velocity is rate of change of displacement, where whatever value of velocity that I have will be the gradient of my displacement time graph. Okay, now for your case here, you can actually see some things here in terms of your value. If you look at the graph like this right now, this one is, what can I say about the y axis value representing value of velocity? This one I can say that v is less and less positive. And then after that, once I go below the x-axis, this one I can say that v is more and more negative. So if I want to translate it to a displacement time graph, the graph that I expect to see ought to be something that looks like this. Wait, let me just try and single out the line here. The graph that I ought to be getting would be something that looks like this. No, it's only a straight line. Actually, with a curve that looks like this. Okay, actually with a curve that looks like this. Okay, so this one here, when I go from here to here, you can actually just say that v is less and less positive. Therefore, gradient is also less and less positive. This is one part. Say number one. Okay, this is number one. There's also another part where B is more and more negative. Therefore, gradient is more and more negative. So part one listed here is referring to this. You can see that looking at the gradient is positive, but it's getting less and less. If you look at part two, gradient is supposed to be more and more negative, which is actually this part here. Okay, it's telling you negative gradient, but you notice that it is actually getting steeper in value. Okay, and this is what more and more negative gradient actually is supposed to be. Okay, right?